Thank you for attending, everybody. We're going to talk about digital twin, digital thread, as we said, and generating synthetic data using AI. I wanted to start with a story. Anybody familiar with the Apollo programs, moon landings back in the 1970s, or the movie with Tom Hanks? Great movie. Okay, one person. Great. Okay, so in the 1970s, NASA, US based, so was driving a lot of missions to the moon. The third mission to the moon was Apollo 13. And unfortunately, on the trip towards the moon, they suffered a catastrophic failure. Their oxygen tanks, something went wrong, there was an explosion, and now they're isolated and stuck in space about 328,000 kilometers from Earth. So we had people, astronauts in space, struggling to figure out solutions to keep themselves alive and safely return to Earth. And then we had engineers on the ground trying to figure out what's the best way to solve the problems, get them back. Through a joint effort, the engineers on the ground were able to figure out different hacks and different solutions to get the astronauts home. And to do this, they used a combination of physical and digital models and simulators so that they could try out and write the procedures and ensure that they could give step-by-step instructions to the astronauts to get them home safely. In 2010, in a report provided by NASA, they coined the term digital twin. That's what we're going to talk about today. So, barring no catastrophic failures for this presentation, hopefully we'll get through a couple introductions and dive deep into synthetic data. So who am I? My name is AJ. I am former Accenture and AWS, currently in the works for piloting an applied innovation studio. I also am a startup advisor and investor, mostly in HCLS, media and entertainment, and real estate. And outside of that, I'm a deep technical wreck diver. So let's get into simulating reality. What is digital twin, digital thread? You can think about a digital twin as a digital representation of a series of complex systems. So the goal of the digital twin is to replicate reality into a very high fidelity set of models. Digital thread, on the other hand, you could think of as all of the different data pipelines that power the digital twin. So collecting all sorts of data from sensors, physics models, anything that you could think of, and stringing that together to then be able to power this virtual simulation. Doing a little deeper dive into digital twin, you could think of it as both a feed forward and a feedback mechanism. And it provides insights into the entire life cycle of a product. So feed forward, what that means is it is designed to influence design decisions. So as you're going through the planning stage, the R&D, the development, think about manufacturing or supply chain. You're building out a new supply chain and logistics network. You begin to input all of these variables into your digital twin model, and from that, it's able to proactively identify gaps, inefficiencies, possible failure points that you need to take care of. Once you get into the actual development and deployment stage, it turns into a feedback mechanism. So you can begin to pipe in all of your data into the model and then begin to predict areas where you're going to see failure points, areas that you're going to see slowdowns, again, in the example of supply chain. You can optimize the solution or the product that you've deployed. And then that goes right back and it keeps looping around. So feed forward and feedback. There's a lot of real world applications. This is used in every day. We just talked about supply chain and logistics, but also things like aerospace, like my example about Apollo 13, agriculture for things like precision farming, cultivating crops, being able to get the highest yield. Financial services, this is a big one that's pretty exciting around fraud detection. So being able to simulate not only transaction data, but also the human behaviors that either are something that are realistic and true transactions or something that could be fraudulent, and proactively identifying those bad actors. This is a article that actually came out 2 days ago. So Desiree Linden, 2018 Boston Marathon champion, is deploying the first digital twin of her heart. So what that is designed to do, again, take in all of the data, understand her biology, understand her competitive abilities and physical fitness markers, and then be able to predict and enhance her training so that she can maximize her physical output in future races. So real world application just came out. I'm really excited learning about this because the human body is incredibly complex, and we are really susceptible to influence from the outside world, your diet, how you slept, just what day it is. And being able to start to simulate that is a huge leap in our ability to simulate reality. So a couple considerations when you start thinking about digital twins is, the goal is to enable safer, more efficient systems. You want to be able to feed that design process so that you can reduce your costs, accelerate your development, and deploy solutions that really solve the real world applications. However, you have to consider that not every solution needs a digital twin. There's a significant cost of entry to this stuff. You need a lot of varied, high quality data in order to drive your digital twin models and to ensure that your simulations are accurate. And this is the type of challenge that we're going to get into right now. So how do you solve for limited data sets, right? When you think of these series of complex systems, there's a lot of corners that we might overlook. There's a lot of areas where maybe we're not thinking about the proper variables. You could think about weather forecasting as one of them. Hugely complex ecosystem of different underlying environmental factors that make up what is the weather going to look like, what's it going to be 5 days from now, a year from now, 5 years from now, things like that. So you're really struggling to get the right data, get it in there, and make sure you're getting a holistic view of that system. So I said data a whole bunch of times, right? So what are we talking about when we think about data? Here's some examples. You have things like unstructured data, so raw text, articles, blogs, things like that, things that are free form. Tabular data, so tables, something that's relational, something that has multiple rows and transaction details, things like that. Time series data, so chronological data, data that you can pull from things like IoT sensors that are time-stamped and have similar labeled data throughout that. Biometric data, big one, and as well as image data, which is becoming more and more relevant, especially as we're deploying things like autonomous vehicles. So we know what some of the data sets are. How do we begin to create data from that, right? So knowing that we need a lot of data to drive digital twins, we need a lot of data in the pipeline for a digital thread. How are we creating that data? How are we supplementing that data? So there's mass data processes, and then we'll get to synthetic data in a minute. Think about a lot of you are developers, engineers, you're building applications, you're testing applications. How many times do you have to do things like creating fake data, right? So that you can go through your workflows and ensure that your algorithms are correct or you're not running into any exceptions. So we've been doing this for years. We've been taking things like production data and trying to remove things like personally identifiable information or anonymize that or build some program to just create data out of nothing. So this was really manual. it had varying levels of success, but a lot of that is changing. So now we're using artificial intelligence to generate high quality, very similar, very realistic data. Let's look quickly at what a generalized workflow is for creating fake data. So both mass data and synthetic data. Typically, you're going to start with some level of real world data. So something that's actually coming from a system that's in place. You're going to go through a process of synthesis where you're understanding that either, you're looking at it yourself, you're writing something to look at it, or you're using a neural network to assess that. And you're going to pipe that in and start creating your synthetic data. But it doesn't stop there. You have to do two things after that. The first thing is you need to validate that type of data. You need to ensure that what you're putting into the system actually makes sense. So in the example of financial transactions, you want those transactions to be as close to real as possible. The other thing that you need to do is you need to assess that data and make sure that none of your original data has leaked through, especially if you're in a situation where you're dealing with healthcare data, right? You don't want any real names to come through associated with real symptoms. You need to be really careful about that. So as we get into what synthetic data is and how we're generated, I want to give a quick recap on neural networks. So very general overview. Neural networks at a high level, you have an input layer and an output layer. And the neural network in between is a bit of a black box that does your computation and synthesis, right? So our job when we think about creating synthetic data is to train those hidden layers so that they understand how to take the input data and transform that into the output data that we're looking at or looking for. So let's go back to synthetic data. There's two main approaches for generating synthetic data, and that is the generative adversarial network and the variational autoencoder. If you were in the previous artificial intelligence talk, you might have heard these two, but we didn't really get into a deep dive of those. So that's what we're going to do now. Generative adversarial networks, right? Let's just think about what the name is. So generative obviously is generating something. Adversarial, so it's fighting with itself. So if you look at the overarching architecture of a GAN network, you can see that there's a generator and a discriminator. These are two different neural networks that are competing with each other. One is generating the data and the fake samples, and the other one is verifying and trying to detect whether that data sample is real or fake. So you can think about it as a painter who specializes in forging paintings. What the generator does, what this painter does, is they look at an original painting and then attempts to reproduce that painting. And that is what we're looking at as that fake sample. The discriminator you could think of as an investigator. And the investigator works at an art museum and is looking at these paintings and trying to detect, is this an original painting or is it a fake painting? And what it does is provides feedback to the generator, to that forger, and says, I can tell you that this is fake. And the generator will go back and say, okay, let me improve my model, let me improve the painting, send it back to the discriminator. And it creates a constant feedback loop until the data, the art that is generated through the generator is nearly indistinguishable from the original, yet still contains none of the aspects of the original. I threw in a little bit of the pseudocode and math behind the generator and discriminator network, and I wanted to close on a couple key things to think about when you're using a GAN, right? Both the discriminator and the generator are trained separately in the beginning. And you define things like the level of noise that is injected into it and the level of iterations that the forger and the inspector are going to go back and forth to generate that data, right? So you're the one who's coming in and saying, this is the original data that you're trying to replicate, and here's how close to that data set you're looking to produce. The second method for generating synthetic data that we're going to talk about is variational autoencoders. So it's a little bit the same where you have a left to right workflow where you have an encoder and a decoder. What the encoder does is it tries to capture the essence of your data set. So think about it as a story, and the encoder is a storyteller. But what the encoder tries to do is to tell the story in as few words as possible without losing any of the context of that story. In this case, take an image and reproduce that image with as few strokes as possible, as few bits of information as possible. So it's almost what it is, but it isn't what it is. The decoder's job is to take this essence that the encoder is putting together and try to reproduce what the story was. Now, there's something called latent space that I want to just touch on, right? Because you see here, encoder, we explain what's happening, decoder, but latent space, what is the latent space? So you can think of the latent space as this compressed zone, right? Where all of the data is coming in from the encoder and existing in some level of fidelity, right? That's where the neural network is really starting to play with manipulating the data. And that's really what your training is. How is that neural network going to take the inputs coming from the encoder and then turn that into some sort of output? And then just like the generative adversarial network, that begins to go through iterations where it's saying, okay, how close to the original is the output? And is that close enough where whatever the use is that we're looking to use that data in is going to interpret it correctly? So a little bit of comparison of generative adversarial networks and variable encoders. Each one has its best use cases. Each one has its fuzzy use cases. So in the case of images, right, you have your GANs that, generator is forging that image. The discriminator is trying to inspect if that's a real image or close enough to the real image. So what you end up because of those iterations is you start ending up with really high quality image data that once again represents the original, but is not the original. So a lot of times GAN networks will be used in creating autonomous vehicle data because you can generate lots and lots of different data sets to train your autonomous vehicles models on without having to capture that yourself. Whereas the variable autoencoder, because it's going through that latent space and just trying to capture the essence of that image, will produce typically blurrier images. If you're looking for something of where does VAEs shine, that's when you have the time series data sets, text data sets, tabular data sets, things where there is some sort of characters that are involved in it. So transaction fraud processing, right? Creating those transactions. VAEs really excel at ensuring that the data is high quality, is capturing what you're looking for out of transaction data, but without bringing that forward. So a little bit of a recap on synthetic data. Generation, there's two primary ways of generating synthetic data. You have your mass data, which is typically produced through a manual process. So developer, like we said, either working with it and manipulating it manually or creating some sort of program that can manipulate the data for them. Or in this case, generating synthetic data using artificial intelligence. The benefit there is, once again, you're getting very high quality data close to the original without it including the original. So you're reducing the potential for privacy information to slip through, or creating data that doesn't quite match the needs of your use case. Some of the benefits is using AI, you can sometimes identify gaps in your data that you're not thinking of, and that AI model, if trained properly, will be able to start to insert some of that data, or begin to point you to, hey, this is going to not work out the way that you are looking to have it work out. So considerations of using AI to create those synthetic data models is cheaper than collecting real world data, right? And this is a huge thing, because if you remember when we talked about digital twins, digital thread, they require a lot of data from different physics models to different inputs from every system in that set of systems. So you have some savings over there. You're able to accelerate the development of your application because you're not waiting to collect those data. You're not going out and implementing sensors, implementing some sort of product or data pipeline to capture the information before you can start using it. Well-trained models, another thing, will be able to produce perfectly labeled models because you're defining what you want the output to look like. And it's going to produce outputs based on your definition. It also minimizes bias. Yes and no. So bias is a big thing in your data, whether it's socioeconomic bias, whether it's trend bias. It could be a lot of things. AI for synthetic data will be able to create that generalized data, trying to pull away from the biases of your real world data. But that really depends on the data sets that you're putting in and the way that you're training your model. It is possible to train the model and have it insert biases into that. So that kind of goes back to the workflow where after you have that synthetic data set, you need to go through and start validating that and ensuring that it is meeting your needs and your expectations. So on the consideration side, garbage in, garbage out, right, with anything. It's not going to fix poorly constructed data and fix just poor fidelity data sets. So yeah, like I said, ensuring the synthetic data doesn't perpetuate its own biases. Privacy considerations, you're going through the validation and making sure that none of the personal identifying information makes it through. So we're going to close on some of the takeaways. Digital twins pushing the boundaries of our understanding of complex systems, right? By thinking through and building these digital representations, as I mentioned, it can point to areas where it's a blind spot for researchers, areas that we're not thinking of, areas that we need to simulate but are too hard to collect data for. Synthetic data, it's the catalyst for refining and supercharging these models, right? Like I said, you're getting a lot of data that's high quality really quickly. And from there, you can stress test your digital twins, you can stress test the models, you can ensure that you are replicating the system in a way that makes sense and in a way that is correctly producing and predicting the outputs and behaviors of that system. We went over GANs and VAEs as two of the primary types to proceed forward and generate synthetic data. And where do you go from here with this information, right? understanding and learning about the process of designing these complex systems and pulling in the different models and pulling in the different data sets and identifying what are the components of a system takes a lot of work. It takes a lot of studying. It takes a lot of time that you're investing in really focusing on every stage of the system set. So you have to spend time doing that. You have to really understand the behaviors that you're going from start to finish. And finally, you have to think about what are the ethical considerations of the synthetic data that you're producing or the digital twin, right? How does that perpetuate bias? How does it demonstrate and predict failure points? How's that going to help to improve the efficiency of a system? So we went a little fast through it. I wanted to give time for questions and make it a little more of a discussion. I think we have about 10 minutes for that. So happy to open it up and kind of dig deeper into the material. I also have a QR code here because it is a heavy topic. I did want to do a broad overview of that. So if you scan the QR code, I have a list of resources that dive deeper into digital twin, digital thread, as well as generating synthetic data, what a GAN is, what a VAE is, as well as a really comprehensive list of videos that you can watch on the topics to kind of pull together some deeper dives of this information. There's also a walkthrough that I didn't present here, but was produced by Amazon Web Services that walks you through simulating and generating synthetic data for financial transactions and fraud detection. So really interesting if you wanted to spend the time and just follow along to try out the procedures for yourself. So with that, turning it over to questions.
Okay, so far we have one question, and I wanted to ask this. Can you share some more success stories or practical applications where the use of synthetic data has significantly benefited organizations or industries?
Yeah.
And other success stories.
Yeah, so a big thing, Amazon uses it to ensure the efficiency of their supply chain, right? You could think of Amazon as world's largest logistics network. So you think about when the COVID pandemic hit and you had a lot of supply chain issues and you had a lot of transportation issues, except for Amazon, because Amazon was able to proactively solve for a lot of those challenges and leverage their own assets and their own capabilities, their own ships that they lease, their own trains that they lease, trucks, last mile delivery. And because they have such advanced models for that and such a deep understanding of where their inventory sits, what is the most efficient and effective way to move inventory either between their distribution centers or to the last mile, they were able to circumvent a lot of the challenges that were faced when thinking about, those supply chain issues that everybody else was facing. So 2-day delivery was still around. Sometimes maybe it was 4-day delivery, but overall, Amazon was still delivering to their promises and getting you the things that you needed as quickly as possible, considering if it was in stock. So some of the paper products didn't really have a choice.
Oh, do we have one more? Can you dig a bit deeper into privacy and misuse considerations? Example would be nice.
Yeah. So I like to use healthcare and life sciences because that's the one that typically contains the most private information. You could also think about banking information for that. So back to healthcare and life sciences, when researchers are trying to consume these large data sets to understand disease progression, the efficacy of new drugs that they're trying to release to market, they're trying to pull real world data, either from actual device data that's coming into them or from observational data. So notes that are coming from MDs that are out in the field that are conducting research and monitoring patients, writing their notes and submitting it. So what comes along with that kind of data? Typically, your name, your age, maybe an address or some sort of generalized location, and a series of biological information. So, what are your other ailments? What medications are you taking? Even what kind of insurance do you have? So you end up with a lot of data that peppered in it has either direct personally identified information or enough information that you can begin to infer things about the population that you're doing the study on. So in that case, using something like synthetic data generated by AI, you're abstracting away the essence of that data, and the data that you're getting output, you have less of a chance to see those breaches of privacy because it can't be tied back to the original data. It has elements, but it doesn't have direct data coming from your input data. So more and more, you're able to move away from your concerns about leaking private information because it just doesn't exist. It can't tie back. And that's opposed to using manual data sanitation techniques, because there you're really dependent on the individual who's manipulating that data. And if they miss something, then you can begin to tie it back. So you perpetuate that problem.
Okay, so we have more and more questions.
Oh,
But we have time, that's good. Aside from utilizing synthetic data for training models and functional testing, are there any existing processes focused on test data for performance testing?
yeah. So some of the things I think about, Netflix was using Chaos Monkey to be able to test the performance of their infrastructure, but also test random failure points. So this is a good example of, as they evolve those algorithms and the understanding of the systems and infrastructure that they were using, it's a good example of programmatically going out there and randomly shutting down services and then being able to understand what is the effect on the services, how does it affect the end user delivery of videos and the experience around that. So yeah, I think there's a lot of ways, not just doing data sets, but also moving in and probing systems and understanding all of the components of the infrastructure, and then being able to just automate the identification of failure points and being able to proactively solve that.
Okay, another question. Are there some techniques to identify bias created by synthetic data in training sets of models other than usage of real data for validation and testing?
Yeah, so there are, unfortunately, I didn't dig into it so much for this presentation, but what I can do in this list of resources, I can start popping in some detailed information so that you can follow up with that.
Good. Another questions. Can you talk about how to prevent AI hallucinations while creating synthetic test data?
Yeah. So this is something that I personally am concerned about, especially when using ChatGPT for almost anything. It really goes into the validation of the outputs and being able to set up some sort of workflow so that you can compare that data with the original. Now, synthetic data at its heart is fake data. So what you're looking at more is the structure of the data set coming out. When you think about the generative adversarial networks, a properly trained discriminator should help identify when the data set is too far off from the original and isn't going to be as useful as you need it in your final application. So that's why both the generator and discriminator you see as being trained separately. And, this is still an area where you as the trainer have the responsibility of making sure that you are using appropriate data sets going in, adding appropriate noise to that, understanding how many iterations back and forth you're going to go, and ensuring that the tested model is going to meet what you need and not have hallucinations that are outside the bounds that you're trying to stick within. Any questions?
There's another about how you see the future. How do you envision the future of AI-generated synthetic data in context of digital twins and digital threads? And what potential innovations or developments do you foresee?
Yeah. So, going back to the example of the first virtual heart, I'm most excited about the leaps that we're making in healthcare and life sciences for that, where we can start to predict things like heart failure, things like medical conditions that are coming down the line, and begin to provide preventative healthcare rather than reactive healthcare. We've been talking about digital twin, digital thread since 2010, right? Well before 2010. We've always wanted to simulate systems. And as I mentioned, the barrier to entry for that has been very high. A lot of times because we just didn't have the amount of data that we needed, or the cost of acquiring that data is just unreasonable for an enterprise to go and embark on that. Now the conversation is coming up again. Now we're able to remove some of that cost, remove the complexity, and really venture into more complex systems, more complex simulations, and do that faster, cheaper, more efficiently, and get more digital twins out there.
Okay, I think we can do also the last one. This is interesting. What about a take on copyright concerns with synthetic data? Are they clear to use, or is there any legal pitfall?
For that one, I think that's another thing that I would need to dig into a little more. Obviously, when we think about Mid-Journey and Stable Diffusion and DALL-E, the question comes up a lot on where was the training data coming from, right? If you're able to go in and say, reproduce a piece of art in the style of Van Gogh, are you actually committing copyright fraud on that? So this is still really a gray area. I think in the case of digital twin and using synthetic data from that, a lot of times you're going to be using your own data. So you're alleviating some of that issue of copyright. But if you were going to use a really broader set, then this is stuff that I think as an industry we're still exploring.
Good. Thank you very much. I think time's up. So that's all. Thank you.